Okay, now we're going to do the lab for chapter 12, which is unsupervised learning, and we'll in particular demonstrate principal components and clustering. So at the beginning of the lab, we import libraries just like we've done before, and by now is very familiar, and some new libraries and functions that get imported as well, including some that have been made for the ISLP package. For the principal components, we're going to work with the USA arrests data, which is actually a data set in the R computing environment. And there's a nice Python function called getRDataset, which can be used to get retrieve data from R packages, and that's what we use here.
That's quite a nice feature in that if you can compare methods in both R and Python. Though we're not talking about R in this course, it's nice to see to be able to compare them. And R has a lot of great data sets built in as well.
And you can see it delivers a data frame, and it's only got 4 variables, which we're using to demonstrate principal components. Principal components ideally, is used to reduce very wide data set when you've got lots of variables, lots of correlations, but here we're just using 4 variables. And the 4 variables look at different crime rates in each of the states in the country. So the rows are states, and the crime is broken down by percent of crimes that are murder, assault, and rape in each state, and actually not percents, but
rates of some kind.
Rates of some kind, yes.
Yeah.
And then there's also a 4th variable, which is the percent of the population in the state that's urban.
Yeah.
So there's the 50 states. So the columns are the 4 variables. We can compute the means of each of the variables. We can also examine the variance of the 4 variables.
Oh, I noticed that there's quite a bit of difference in the variance there. I wonder if that might make a difference in the principal components.
Yes. So principal components like ridge regression and lasso, it's an unsupervised learning method, but it's sensitive to the scaling of the variables. It's looking for linear combinations of the variables with large variance. If we just used it on the data as is, you can see the assault variable, which has a large variance on its own, is going to get a lot of weight in the components because it's got high variance. So what we usually do is standardize the data, and we're going to use our standard scalar again with standard deviation and with mean. So we're going to center the data and standardize to have each of the variables have unit standard deviation. And we've defined the scalar, and then we do a fit and transform on the USA arrests, and we give ourselves a new data frame, USA arrests _ scaled. Now we're going to perform principal components on them. And so we define PCA US as this PCA function from sklearn, and we fit it on the USA arrest scale data, and that's computed our principal components for us.
So, Trevor, I noticed here that the fit method, it just seemed to take an X matrix, and I guess that's because this is a transformer instead of an estimator. Like a classifier would have or a regression would have a label, right?
Yes.
Yeah.
I see. Good point. Yeah. So that reminds you that principal components is unsupervised, so there's no response. Mm-hmm. We can compute the mean of the principal components. This gives you the means of the variables, and we see that they're all 0 as we expect because we did the centering and scaling.
Yeah. So I think what a PCA might, if you had not standarded it itself, it would standard it for us, and we might see non-zero. But we already removed the mean. So.
Yeah. So now, having computed the principal component, you can extract things such as the scores. Those are often what we're interested in, and we get those by using the fitted principal component model to transform the data matrix the data frame that we provided, and that gives us transforms to the principal component scores. Okay, and then the components are the direction vectors that define the principal components. Now we've got 4 variables in our data frame, so we can get at most 4 principal components, and here we've computed them all. And the rows of these components are the direction vectors. So how much weight to give to each of the 4 variables. So each row is a different principal component. So one of the things we like to do with principal components is plot the data, and in particular plot the leading principal components. And it's often common to make a 2-dimensional plot because that's something you can visualize nicely. And so here we set up some code for doing that, and labeling the axes and so on.
Sure. I think this one, you might see this called a biplot in some place. Is that right?
It's called a biplot. Yeah.
Okay.
And let's just look at the plot, and you'll see that code produced this plot here. And the reason it's called a biplot is because it's both plotting the principal components, it's also plotting these little line segments here is showing, is representing the coefficients of the directions. Right? So you see them both in one plot. Now, so that's the code for producing this plot. If you look in the textbook, you'll see the biplot for the same data, that this picture is upside down relative to that picture. And that's because the scores in the principal component, you can multiply any of the scores for any of the components by -1, and the variance doesn't change. And principal components is all about variance. So principal components gives you a solution up to sign flips on each of the components. So we can redo this plot by flipping the sign on the second component, and we do that, and that gives you a picture that looks exactly the same as the one in the book. We've also applied a bit of scaling to the little line vectors to make them occupy more of the frame, the plotting axes.
So I'm wondering how to interpret. So it looks like the urban pop is sort of vertical. So maybe this axis is separating population states by how urban they are, and then the left-right seems to be sort of like a violent crime or not axis. Is that how it is?
That's exactly right. Yeah, and that's exactly what you do, Jonathan. You look to see for each of these variable lines how aligned they are with either of the coordinate axes in these plots, and that helps you name the plot. So in this case, it gives you a very nice interpretation. And there's various other things you can extract from the fitted principal component object. One thing people like to look at is how much variance is explained by the components, because you're trying to do a data reduction, okay? And so we're interested in the variance, and so what we have here is this actually computes the variance of each of the components, and they necessarily must be decreasing, because the first principal component has maximum variance, the next one second maximum, and so on. And because the data was standardized, these variances must add up to 4, because the original variances were 1 for each of the variables, and a property of the principal components is that the sum of the variances of the solutions give you the original sum of variances. What's often more interesting is the percent variance explained, and so that we've computed at the bottom here. And you see that the first principal component explains 62% of the variance. The second principal component explains a further 28% of the variance. And then the remaining 2 principal components explain much less.
Quite small.
Yeah. So we're going to make a plot to show both the variance explained and the percent variance explained. And this plot is going to have 2 subplots, because we're going to have 2 plots in a row. Okay. And so what we've done here is we first produce the first plot. That's code for the first plot, which is proportion of variance explained. And then in the second plot, it's going to be cumulative proportion of variance explained. And we want to plot them both. And so what we've done here is we've used this percentage capture, which lets you produce a plot but not display it right away, just hold it. And then you can add your second plot, and then you can display the whole figure, which you just do by typing fig. And so there you see the two plots.
Yeah, I guess without that capture, we would have, after the first line, we would have seen two plots. Well, the one on the left would have the variance ratio, but we wouldn't have filled in the second one.
And it would be blank, would it?
Yeah, it
would have been blank.
We haven't plotted anything to that axis.
So that's a way of doing them both.
And I'll just say this percent, these things are called magics. So there are various, percent capture is one of them, but there's some handy ones. And actually, we mentioned R a little bit earlier. You can actually there's an R magic that you can run R code in Python. We're not going to talk about it today, but that's these magics of IPython.
Okay. So that's the end of principal components. We're going to leave you to read the section on matrix completion, where you can use matrix principal components as a means for filling in missing data in a data matrix. But we'll leave that for you to do on your own.